This lesson is going to look at how systems of equations can be represented graphically. We'll start with linear equations, and throughout this lesson I'm going to use matrices. To write this pair of equations in a matrix, I put the coefficients of x and y and then the constant term on the right hand side, and the same for the second equation. And I'm going to perform some row operations to get my matrix into row echelon form. Firstly, I'm going to swap row 1 and row 2 around because it's nice to have a 1 in the top left hand corner. Then I'm going to replace row 2 with row 2 take 2 lots of row 1. So this is telling me that negative y equals negative 1, which means that y is 1 and x plus y is 3, and therefore x must be 2. Now let's think for a minute what that means graphically. These two equations are both linear and both represented by a line on the graph. Here are the two lines. The red line is 2x plus y equals 5 with its intercepts at 0, 5 and 2.50, and the blue line is x plus y equals 3 with its intercepts at 3, 0 and 0, 3. And where the two lines cross, you can see is at the point 2, 1, which takes us back to our solution of x equals 2 and y equals 1. So graphically, the simultaneous solution of the two equations corresponds with the point where the two lines intercept. So in example number 1, in matrix form, in row echelon form, we ended up with 1, 1, 3, 0, negative 1, negative 1, and graphically this is represented by two lines intersecting at the point 2, 1. So we have a unique solution. Let's have a look at example number 2. And I don't have a 1 in the first column, but I can achieve a 0 in the first column of row 2 by replacing row 2 with row 2 take row 1. But unfortunately, in eliminating the coefficient of x, I've also eliminated the coefficient of y. So this is telling me now that 0x plus 0y is negative 2. That's just not possible. And even looking at the original equations, whichever values you choose for x and y, there's no way that 2x plus y can equal 5, and at the same time 2x plus y can equal 3. So let's think about what that means graphically. Here are the two lines. The red line is 2x plus y equals 5 and the blue line is 2x plus y equals 3, and you can see that these two lines are parallel. They never cross. If we go back to the original equations and put them into gradient intercept form, this would be y equals negative 2x plus 5, and the second one is y equals negative 2x plus 3. They both have the same gradient of negative 2, so they will never intercept. Two parallel lines means the equations are inconsistent. There is no solution, there's no x and y values that are true simultaneously for both of these equations. What that means when we look at the matrix is that we have 0 coefficients of x and y in the same row as a non-zero constant. So we're saying that when we multiply x and y by 0, the result is something other than 0. Clearly that's not possible, and what that means graphically is there is no point of intersection between the lines. In the third example, we have a third variable z as well as x and y. So I'm going to solve the simultaneous equations using matrices first, and then we'll think about what the graphical representation of it will look like. Here are the equations in matrix form. There's already a 0 in column 1, so I'm part way to achieving row echelon form. There's no 1 in the first column, but I can replace row 3 with 2 lots of row 3, take 3 lots of row 1. So that's where my 0 comes from. Finally, in order to achieve my third 0 for row echelon form, I'm going to replace row 3 with row 2 plus 2 lots of row 3. So I've achieved row echelon form, and now I can substitute the variables back in. So negative 9z is 27, means that z is negative 3. And then in the second row, 2y plus z, which is negative 3, is 1, so y is 2. And then in the first row, 2x plus y plus z equals 1, so x is 1. Graphically, because we now have a third variable, we're operating in a three-dimensional space instead of a two-dimensional space. And our equations represent planes rather than lines. So that first equation in the previous example, 2x plus y plus z equals 1, looks like this. And the second equation, 2y plus z equals 1, intersects the first plane. And you can see it intersects along an infinite number of points. There's a line created here between the two planes. So what happens when we add the third equation, 3x plus y take z equals 8, and the third plane intersects the first two planes, and you can see that it intersects at a single point here. And that single point corresponds with the solution we found. In three-dimensional coordinates, that solution is 1, 2, negative 3. The x value of this point of intersection is 1, and the y value is 2. And if I change to a three-dimensional view of the axes, you can see that the z coordinate of that point is negative 3. So our graphical representation of these three simultaneous equations is that we have three planes intersecting at a single point and therefore one unique solution to the equations. Using matrices, we managed to reduce the matrix to row echelon form and find the coordinates of that point. And graphically, we can see the three planes intersecting at that single point. I'm going to work through several more examples, in each case using matrices to try and reduce the system to row echelon form, and then to have a look at the graphical representation of the equations. If you're feeling confident with solving the equations using a systematic method, then please pause the video and try these for yourself before watching my solutions. So in example number 4, here's the matrix form of the equations, and I'm going to perform two row operations at once. Row 1 remains unchanged. I'm going to replace row 2 with row 2 plus row 1, and replace row 3 with row 3 take 2 lots of row 1. So you can see in this system I've ended up with two rows consisting of coefficients of x, y and z that are 0, but non-zero constants on the right hand side. This is the equivalent of saying 0x plus 0y plus 0z is 13 and 0x plus 0y plus 0z is negative 3. Clearly this is impossible. And if we look back at the original equations, you can see that the coefficients of the second and third equations are multiples of each other. So if we number these equations 1, 2 and 3 and multiply equation 2 by negative 2, we get the same coefficients of x, y and z, but different constants on the right-hand side. It's similar to the example with the two parallel lines, where we had 2x plus y equaling different constants. And in actual fact, that's what we get in three-dimensional space. Parallel planes instead of parallel lines. And there's a similar relationship between equation 1 and equation 2. If you take equation 1 and double it, we get the same coefficients of x, y and z, but a third different constant on the right-hand side. So this solution is inconsistent. There's no point in three-dimensional space at which all three of these equations hold, and graphically this will look like three parallel planes. Here's example number 5 in matrix form, and I'll perform a couple of elementary row operations to see if we can solve the system of equation. So replacing row 2 with row 2 take row 1, and replacing row 3 with row 3 take 2 lots of row 1. So you see this time we've ended up with a row that consists of 0 coefficients of x, y and z and then 3 as a constant, and a whole row of zeros. Let's think about what this means graphically. We know that if we've got 0, 0, 0, 3, that's impossible. The system is inconsistent. There's no solution which is true simultaneously for all 3 equations. In other words, the planes represented by the first 2 equations are parallel. But what about this row of zeros? If we have 0x plus 0y plus 0z equaling 0, that actually has an infinite number of solutions, because it doesn't matter what x, y and z are, this equation is always going to be true. And the reason for that is equations 1 and 3 are 2 equations for the same plane. So graphically, the 3 equations look like this. 2 of the equations represent one plane, and then the third plane is parallel. And so there are no solutions because there is no point which is on all 3 planes. In example number 6, I've written the equations in matrix form, and then I'm going to replace row 2 with row 2 take row 1, and row 3 with row 3 take 2 lots of row 1. And again we've reached a row consisting of zeros and a 1 constant. So we know that this system is inconsistent. Let's have a think about why that might be the case. If you look at equation 3, the coefficients of x, y and z are the same as equation 1 multiplied by 2. So we know that equations 1 and 3 represent parallel planes. The second equation is consistent with the other 2. So what we'll have graphically is 2 parallel planes and then a third plane which intersects them both. So here you can see those 2 parallel planes, the red plane and the green plane, and intersecting them both is the purple plane. In example number 7, we have the matrix form of the equations, and then I'm going to replace row 2 with row 2 take row 1, and row 3 with row 3 plus row 1. And we're not quite in row echelon form, so I'm going to perform one more row operation, which is to replace row 3 with row 3 plus 2 lots of row 2. And now I've got another inconsistent system with the 0x plus 0y plus 0z equals 2. And this time, none of the original planes is parallel. We have an intersection when y equals 1, and when y equals 1, substituting into row 1, we have x plus 1 take z equals 1, or x equals z. So we have an infinite number of solutions connecting the first equation and the second equation along a line where y equals 1 and x equals z, but the third plane doesn't intersect along that line. So when we look at the graphical representation, you see that each pair of planes intersects, but at no point do all 3 planes intersect. The 3 planes intersect in pairs, and the lines of intersection between the pairs of planes are all parallel to each other. In summary then, each of these 4 systems of equations had no solutions. When using matrices and elementary row operations, what all 4 of these had in common is that the system reduced to a row consisting of zeros and then a non-zero constant, which is impossible. 0x plus 0y plus 0z is something other than 0. So we can establish without drawing the graph if we can reduce the matrix to a row consisting of zeros and a non-zero constant.